A quick word then about series and parallel and what we mean by series and parallel. So, firstly then, what we mean by series. Well, let's take a single resistor, 4 ohm resistor, don't worry about the numbers, and let's say we've got a 12 volt supply. Now, here we have a complete circuit, and so the current, which we use the symbol I for, but don't worry about that, the current is flowing around the circuit. Whatever current flows into this point has to flow back out of it again. So all of the current that flows out of the battery flows around the circuit. It all flows through this resistor and back out to the battery again. So let's then consider 2 resistors in series. Now, same idea. Here we have if we had 12 volts. Again, all of the current that flows out of the battery flows through this 4 ohm resistor and this 4 ohm resistor. This is a series circuit because all of the current that flows through any one of the things in the circuit flows through all of the others. That's what makes it a series circuit. There is nowhere else for the current to go. It can only go in here, out of here, in here, out of here, and so on. That's it. It can't do anything else. So that's a series circuit. And the current everywhere in a series circuit is the same. Now, if we compare this circuit, where there are 2 4 ohm resistors, to the previous circuit, where there was only 1, then if this is also 12 volts like we had in the previous circuit, then because we have less resistance here, it is easier for the current to flow here than in this one. Because it is easier, I'll just get rid of those 2. It's easier for the current to flow in this one than in this one. Then the current in this one, assuming that they're both 12 volt batteries, the current in this one will be smaller. In fact, because we've got 2 4 ohm resistors, one after the other, in series, rather than just one 4 ohm resistor, the current in this circuit will be half as big as the current in the previous one. Okay, so that's a series circuit. Two things then about series circuits. One, the current is the same everywhere. In a series circuit. And 2, the total voltage across everything in series equals the voltage across the battery or the power supply or whatever. Let me show you what I mean by that or why that has to be. So let me just get rid of all that I just wrote. Okay. I can't do that, but I will do a different thing. So, if we've got 12 volts across here, so the battery PD, potential difference, voltage, is 12 volts. That means going from here to here, the current flows this way, you gain 12 volts. This is about energy. And you'll know that energy cannot be created or destroyed, simply changed from one form or store to another. This is the energy per unit of charge moving around the circuit. So you know there are charges moving around, the current is a flow of charge. This is the amount of energy being gained going through the battery by each charge, each unit of charge. So if you gain 12 joules of energy for every unit of charge as you go through the battery, then as you come back to the battery, having gone around the circuit, you have to lose the same 12 joules for every unit of charge. 1 volt is 1 joule per unit charge. More of this when we look at it in year 10. So, because these two are equally difficult to get through, you're going to lose half of the energy for every unit of charge there and half of the energy for every unit of charge there. Now, if we had just the one resistor in there, then the whole 12 volts would be dropped across that one resistor. So if I took away my 2 4s and I put in a single 4 ohm resistor, then we wouldn't have 6 volts and 6 volts like we had before. The whole 12 volts would be dropped across that one resistor. So, 2 things about the series circuit. The current everywhere is the same in a series circuit, so wherever I was to measure the current around this circuit, I would find I got the same answer, because there's nowhere else for the current to go. If it goes in here, it has to come out of here and go in here and so on. So the current will be the same everywhere. And with your power supply, your battery, whatever, you have, let's say, 12 volts across it, which means that you will gain 12 volts going this way. And because energy can't be created or destroyed, and voltage is about energy, then when you go from here back to here again, as you come round the circuit, you have to lose those 12 volts you gained. That's the rule, that's the law. So if you've only got one component, one resistor, bulb, whatever, then all 12 volts will be across that. If you've got 2, then some will be dropped across one, some will be dropped across the other. The total will be 12 volts. And how much is dropped across each depends on how difficult they are to get through. So if they're both equally difficult, half of this 12 volts will be dropped across each of them. If one's twice as difficult as the other, then twice as much will be dropped across that. And that means it's in thirds then. So if you had, for example, 8 ohms and 4 ohms, well, this is twice as difficult as that, so twice as much would be dropped across that, so that would be 8 volts and 4 volts. If I made that 10 and 5, the same thing would happen. That's twice as difficult as that, and so twice the amount of voltage is dropped across this one compared to that one. So that's a series circuit. Let's then look at parallel circuits. So let's turn off what I've got. And if we then have, let's say, 2 resistors in parallel. And we have our 12 volts across them as we had before. So, what we said before was when the current comes around the circuit, all of it had to go through one and then the other. Well, here, when the current gets to here, it splits. Some of the current goes that way, some of the current goes that way. But again, whatever comes into this arrangement of 2 in parallel has to come back out again. So the same current that flows in here has to come out here. But some of it will go that way, some of it will go that way. And how that division is made depends on how difficult these are to get through. If you imagine, in an extreme situation, if I put another one in here, if I made that one of my parallel branches, well, this is a break in the circuit, right? This is a hole. So this is a massive resistance. This is really, really hard for the current to get through. Whereas if I was to go to the other extreme and I just had a piece of wire in there, well, that's really, really easy. So virtually all of this current would go that way. None would go this way because this is really, really hard. A little bit will go this way and a little bit will go that way, because even though this is really, really easy, current can flow through these two, just not very much. So how much current goes through each of the branches just depends on how difficult it is to go through each branch. The easier it is, the more of the current will flow through that easier branch. That's how it works. So that's your potential difference, your voltage consideration. Let's think then about the potential difference, the voltage. Sorry, I said voltage, I meant current. We've talked about the current. Let's talk about the voltage now. So let's have three resistors in parallel, and let's apply the same idea that we had before on the series circuits. So let's say that's 12 volts again. Remember we said that what that means is 12 volts gained going through the battery this way, and therefore a total of 12 volts lost in coming back around the circuit. Now, it doesn't matter which way you go. You will lose the same amount of energy whichever path you take. If you think about this in terms of climbing a hill, so let's say it's a cliff. You're down here at the bottom of the cliff. When you climb the cliff, you have gained height, but that wasn't intentional. You're now taller than you were before. When you climb the hill or the cliff, you've gained some energy. You are now higher than you were before, and so you have gained some gravitational potential energy. Now, it wouldn't matter whether I had a set of steps up the hill, up the cliff, or whether I was to attach a rope and climb the cliff vertically. It wouldn't matter whether I went from here to here, via Hong Kong, and then come back to the top of the cliff. I started here, I finished here, and I gained the amount of gravitational potential energy that is down to this change in height. That's how it works. The same thing happens here. When you go from here to here, you will lose the same amount of energy. It doesn't matter whether the current goes through this one, or this one, or this one. Going from here to here, 12 volts will be dropped.